Over the next few videos, we will discuss Newton's 3 laws of motion and learn how to apply them. In this video, I'll set the stage by briefly describing Newton's first and second laws, and then discuss mass and net force, which are integral components of these laws. So let's start with Newton's first law. It's stated in a variety of ways. Here's one way of stating it. An object at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted on by a net force. So as an example, if a rock is moving through space at 100 miles per hour, and it is far enough from other objects that it doesn't experience a force, then it will continue to move at 100 miles per hour in a straight line indefinitely. Or if the rock is at rest, which is to say that its velocity is zero, and again is far enough from other objects that it doesn't experience a force, then the rock will remain at rest indefinitely. So that's Newton's first law. Newton's second law is this equation: F net, or the net force, equals mass times acceleration, where F net is the net force acting on an object, and as a reminder, the SI unit for force is a Newton, and m is the mass of the object, and the SI unit for mass is a kilogram, and a is the resultant acceleration of the object, and its SI units are meters per second squared. Newton's second law is one of the key concepts in Physics 1, and while the equation may appear simple, it embodies several important concepts. The first one, regarding the relationship between net force and acceleration, is that net force causes acceleration. So this is a cause and effect relationship, where the presence of a net force on an object causes the object to accelerate. Tying this into our previous discussions on kinematics, we can now see that the acceleration that was involved was present because there must have been a net force acting on the object. The next concept, still considering the relationship between net force and acceleration, is that if one is present, then the other is present. Or conversely, if one is zero, then the other is zero. We can see this in the equation. For example, if F net is not zero, which is what is meant by it being present, then mathematically, the acceleration cannot be zero either. Or if F net is zero, then the acceleration must also be zero. A third concept, again still considering the relationship between net force and acceleration, is that they are always in the same direction. This is also expressed by the equation. Since it is a vector equation, not only do the magnitudes of the left and right sides of the equation need to be equal, the directions need to be equal as well. So that means that the direction of F net must be the same as the direction of the acceleration. The mass doesn't factor into the direction aspect of the equation since mass is a scalar quantity. The next concept is that Newton's second law actually explains Newton's first law. This is basically how: start with the second law, and then recognize that acceleration is defined as the change in velocity over the change in time. So making this substitution, the equation becomes this, and that means mathematically, if F net is zero, then delta V must also be zero. Delta V is the change in the object's velocity, so if it's zero, then the velocity is not changing, or in other words, the object is not changing speed or direction. And this is what Newton's first law essentially says. And then the last concept we'll extract from Newton's second law is a definition of mass. Conceptually, mass is an object's resistance to acceleration. If the same net force is applied to two objects with different masses, the object with the smaller mass will accelerate more than the object with the larger mass. Galileo referred to this as inertia, so conceptually, the terms mass and inertia refer to the same property. Mass is also defined mathematically by Newton's second law. If an object is at rest and a net force of known value is applied to it, we can then measure the resultant acceleration and calculate the mass by solving Newton's second law like this. And then to be complete, as was mentioned before, the SI unit for mass is a kilogram, and mass is a positive scalar. Some scalar quantities like temperature can be signed, but mass is always a positive value. Now let's talk about forces and net force. First, the basics. In colloquial language, a force is a push or a pull between two objects. Notice there must be two objects, which means an object all by itself cannot experience a force. There must always be another object that causes the force. Examples of forces are force by gravity, force by the floor, force by the air, force by a rope, force by a person, and this list could go on pretty much forever. Notice it's often instructive to name a force based on the object that causes it. And we'll usually do that, but not always. For instance, the first one in the list, gravity, is not named for the object that caused it. If it were, it might be called the force by the Earth. Most of the forces we deal with require physical contact, like the bottom four forces, so we call them contact forces. A few forces, like gravity, the electric force, and the magnetic force, interact at a distance via a field, so we call them field forces. Later in the course, when we start talking about energy, we will categorize forces by whether they are conservative or non-conservative forces. We'll discuss what these terms mean when we get to that point. And then two more things we've already mentioned are that the SI unit for force is a Newton, which is a kilogram meter per second squared. And it's also useful to know that 1 force pound is equal to 4.45 newtons. And then the last fact for this list is that force is a vector. Now let's talk about finding the net force on an object. As the name implies, the net force is the sum or the total of all of the forces acting on an object. The keys to calculating the net force on an object correctly are to first identify all of the forces acting on the object, and second, to add the forces with proper vector math. So let's try this in an example. A crate is being pulled across the floor as shown in the picture. We're first asked to draw all of the forces acting on the crate. Drawing all of the forces acting on an object is an important first step when applying Newton's second law. We're actually getting a little ahead of ourselves since we haven't discussed forces like friction in detail yet, but I want to mention this step since it will be critical for us as we begin to apply Newton's second law. A good technique to make sure you have identified all of the forces and don't miss any is to consider all of the other objects in physical contact with this object, and then add the force of gravity if applicable. Based on that statement, the rope touches the crate and causes a force. Air touches the crate and causes the force of air resistance, but in this situation it's so small that we'll neglect it. The floor touches the crate, which actually causes two forces, one pushing straight up, and it also causes the force of friction. And then the force of gravity is also acting on the crate. And now I'll show all of these forces acting on the crate, and I'll include values as well. Don't worry how I knew to draw these force vectors in the direction shown. As I said, we'll discuss several of these forces in more detail later. One general technique I'll mention, though, is that when drawing vectors, it's often convenient to put the tail of each vector on the object as I've done in this picture. It's not a requirement, but it often helps to keep the picture organized and will help when calculating the net force, which is the next question in this example. Given the force vector shown, find the net force on the crate. Okay, so we need to add up these four vectors. We'll use the usual coordinate scheme shown here. And now I'll clear the screen and list the four vectors in preparation for adding them. I put them in Cartesian form since we'll be adding these vectors. And now let's put in values. As was shown in the previous picture, the force from the floor is 300 newtons in the positive y direction. The friction force is 50 newtons in the negative x direction. The gravitational force is 400 newtons in the negative y direction. And since the force by the rope is at an angle, we need to calculate its components. Here's the right triangle for the vector, and here are the trig functions to calculate the components, which come out to be 173 newtons in the positive x direction and 100 newtons in the positive y direction. So I'll add these values to the vector list. And now we can add up all of the individual components to get the components of the net force, which are plus 123 in the x direction and 0 in the y direction. Or we can easily write it in polar form, 123 newtons in the positive x direction. Is it a coincidence that the y component came out to be 0? Think about that and we'll discuss it in class. So that's it for this video. In the next video, we'll begin to apply Newton's second law to various situations. See you then.